Hey everybody, welcome back to Grade 12 University Physics, here with Mr. Stone. So we're going to talk about now some really fun stuff. So this is now going into our last unit on modern physics. So we're going to now step into basically the 20th century, not quite 21st century, but we're going to start looking at some of the big ideas that have revolutionized physics, our understanding of the universe, really, that have happened in the last 100 years, looking at relativity, quantum mechanics, understanding the atom, a little bit of nuclear physics even. So we're going to try to figure some of these bigger ideas out. So if you were, let's say, a physicist going into university, and let's say this in like 1900 or so, and you said, I want to study physics, people would probably think you're wasting your time, because at that point it was understood that physics was over, that we basically figured out everything. Newton had done his work 300 years ago at that point, and we develop all this classical mechanics, looking at things like Lagrangians, and we'd figured out pretty much what they thought was everything. There was only a few unanswered questions that people were still looking at, and once we figured out these last few couple things, right, we let's go back quickly. Right, we did in last unit, we looked at electricity and magnetism. Right, they'd unified those. We'd understood electricity and magnetism. It all made sense, right? Other things in physics that we figured out most of thermodynamics, in terms of statistical thermodynamics type stuff. We'd figured all this stuff out. There's a few things that were still confusing though. One of the big ones about light that was confusing everybody was, what does light travel through? For a wave to travel through a medium, it needs a medium, right? Water, without the water, there's no water waves. Without air, there's no sound. So what does light travel through? We hadn't figured that out yet. That's what we were looking for at this point. So almost all physicists thought that we needed to look for some sort of what they called a luminiferous ether, something that light would be able to propagate through, something that this disturbances in the electric and magnetic fields would actually be in. Okay. The other one that was confusing to everyone was, how come atoms don't collapse? They'd found electrons, looking at heating up metals, and found these negative particles that were being thrown off of them, or was coming out of it. They called them electrons. This was J.J. Thomson and his Crookes tubes, things like that. And they existed in the atom. And at this point, they thought that maybe they sort of were spinning around them like a little tiny solar system. This is the typical picture that we see of an atom. Like, there's the nucleus in the middle, and then there's these electrons that fly around it. But that caused a problem, because as an electron flies around, spins, right, it's going to have to be under some influence of a centripetal force. So we're accelerating inwards an electron. Anytime we accelerate electrons, they should be giving off energy. That's just the nature of moving charges. Moving charges generate electric fields. We saw that, right? That was Faraday's law. Now, if they're giving off electromagnetic radiation, that's some energy. So they'd be losing a certain amount of energy. As it loses energy, it should slow down. Its radius should get smaller and smaller and smaller, until the electron, if it's a charged electron spinning around the atom, it should quickly, and we're talking very, very quickly, 10 to the negative, I think it was 47 seconds, some almost instantaneous time in which the electron would crash into the nucleus, right? Because it's a positive nucleus and a negative electron. There's also an electromagnetic force pulling them together. And why doesn't this happen? Why doesn't all matter collapse? Really, this is saying that the universe shouldn't exist. There's something we're missing. There's some theoretical understanding of the atom that we're missing, that doesn't allow the entire universe to collapse in 10 to the negative 47 seconds or something like that. So that was another unanswered question. Why doesn't the atom collapse? And the other one that was when they were looking at thermodynamics was the black body curve. We saw this in the last lesson of Unit 4. We called this the Boltzmann distribution that showed what colors are produced by a black body. Right? We start off with cooler things, or sort of they start glowing red, then they glow orange, then they glow white, and then eventually they'll even glow into the ultraviolets. Unfortunately, nobody could explain why. Everything that had shown this black line here, this is called the Rayleigh-Jeans law. You don't have to know that, but that was the understanding of what atoms would do from a classical point of view. That's from a Newtonian point of view of atoms bouncing around or being on sort of like springs, thinking of them as atoms in a material. They're sort of stuck together and they're sort of springing next to each other. And we came up with this curve. And as you can see, this curve is asymptotic. As we get smaller and smaller wavelengths, we should have, brighter and brighter light. For some reason, everything starts collapsing once we get into this ultraviolet region. So this was referred to as the ultraviolet catastrophe. We had no way of explaining what's happening in these lower wavelengths. Okay, so these are three. They didn't think these were big questions at the time, but these are three pretty big questions from our from what we can look at, looking backwards in retrospect, right? And that's what we're going to try to answer in this unit. We're going to try to go through the development of modern physics from 1906 or so, and try to figure out some of these questions. So let's start with this luminiferous ether problem. So at that point, it was accepted that there was some medium that permeated the universe, some sort of thing that's everywhere in the universe. And this is the medium in which light travels through, the luminiferous ether. Light somehow goes through this stuff. And the idea was that if there is this medium and the Earth is moving, right? The Earth is spinning around the sun, and the sun itself is moving in the solar system. There must be some relative motion of the Earth to the ether. And if we are able to see a difference between, let's say, at some point here where the Earth is at this point, this is now going against the ether, and at this point it's going with the ether. So think of it like waves in water. If we're moving with the water, the waves should go slower. If we're moving against the water, the waves should go faster. So the speed of light should be changing as we go through the year. There should be some. It might be very, very small. Right? And the speed of light they'd figured out by Maxwell's equations. Speed of light is very, very fast. 3 times 10 to the 8 meters a second. So we have to do some very precise calculations or experiments of wavelengths and this to start trying to figure this out. So for us to find this ether wind, as they call it, if the ether permeates the whole universe, then due to Earth motion, there must be some detectable ether wind. Assuming that the speed of light would change in different directions relative to the wind, it should be possible to measure the motion of the ether. So we're trying to look for this ether by looking at the changes in the speed of light. So what they came up with was this thing called the Michelson-Morley experiment. This apparatus is called a Michelson interferometer, and it had been used to calculate wavelength of light. How it works basically is you get a light source. Let's say it's a monochromatic light source. For example, nowadays we'd use a laser. There were no lasers in the early 1900s. You could use something like a sodium lamp. Sodium produces very, very bright yellow light. That's a very particular wavelength. So we're going to use some sort of monochromatic light source. And we're going to send it into this mirror. But it's a special kind of mirror called a beam splitter. And it's a mirror that lets half the light through. It reflects half the light. So half the light's going to go up to this mirror at the top and bounce back. And then when it hits the beam splitter, it's going to go through. So we're going to have one path here that's going to be vertical. And then there's going to be another one that's going to just pass through. So 50% of the light is going to go up, 50% of the light is going to go through, hit another mirror, come back, and bounce back and hit to the screen. So we're going to have the light being split, and then coming back together. And if you do this very carefully, you should see interference here. Because if there's any difference in the lengths of these paths, it'll change the phase. So you can very carefully, if you put one of these mirrors on a very precise slider that can go back and forth very, very small distances, we can calculate those very, very small distances by looking at the phase change on this screen. What you end up seeing is something like this. This picture. Sorry. Where are we? Why is it not going? Why is it not going? All right. 1 second. I just want to turn off my camera for a sec. All right. So this picture here shows us the fringes as they change. These are called the fringes. This is the diffraction pattern, the interference pattern that happens between the two paths of light. Okay, so our paths are two different phases as they go. They go in and out of phase. So you can look in the center here. That it's bright and then it's dark. So as the path length changes we're talking at 10 to the negative 7 meters, we can see nanoscale motion. So they tried this experiment a bunch of times, and they tried it in different parts of the world. They tried it at different seasons. They put the whole thing on a very precisely balanced bed of mercury liquid, and that the whole thing was on a slab of concrete, so that everything wouldn't move. Everything was very precise. And remarkably, there was no change. Okay? Remarkably, there was no measurable difference. So they failed. They couldn't do it. They couldn't find the ether. So this is so far, has become known as one of the most famous failed experiments, because there is no ether, and the speed of light has to be constant everywhere. Okay, so we couldn't. There is no luminiferous ether. But the problem here is a little bit confusing, because, right? Let's say we have two cars coming towards each other. We've seen this before, right? This is relative motion. If I have an 80-kilometer car coming to the right, an 80-kilometer-per-hour car coming from the left, if you are sitting in the car, you see a car coming towards you at 160 kilometers per hour. Makes sense, right? From the stationary frame of reference of the left car here, for example, if I'm at a frame of reference outside, I see 80 left, 80 right. From the inside, I see 0 motion for the left car, if I'm inside the left car here. But I see a car coming at me at 160 kilometers per hour. But let's say I have two rockets that are approaching each other at 80% of the speed of light. That's what this is saying here. 0.8 c. C is the speed of light. So this is 80% of the speed of light. An outside observer, so me standing here, will see two rockets coming towards some central point at 80% of the speed of light. But if you're in the rocket, you're going to see a rocket coming towards you at 1.6 times the speed of light. And we can't do that. We said that the speed of light is constant. So for example, think about if you had a flashlight and you were sitting in this rocket and you had a flashlight and you pointed it at a person on the other rocket here. The light that was emitted from this left-hand rocket would be traveling towards the other rocket at a 1.8, like 1, right? It'll be leaving here at the speed of light, some flashlight here. And then that we'll have to add to that the speed of the rocket. So you'll observe, this observer here in this rocket will observe the speed of light at 1.8 c, which doesn't make sense. We can't go faster than the speed of light. We can't have a change in the speed of light. So Albert Einstein shows up and has a remarkable, very simple solution to the problem. The problem with this solution is not the simplicity of it. The solution is simple. The implications of the solution are very complicated and change everything. Change the entire understanding of our universe. His postulates of what we call Einstein's special relativity. There's another level to this called general relativity, which is a bit more complicated. We're not going to get this. So we're talking 1906. Okay, this is the postulates of Einstein's special theory of relativity are: number one, all laws of physics are equivalent in all inertial frames of reference. Right, we've already said this basically. This is a very Newtonian idea that the laws of physics are the laws of physics in every inertial frame of reference. He went a little bit farther and said that the speed of light is also the same in all inertial frames of reference, regardless of the velocity of the observer or the velocity of the light source. So the speed of light, no matter how you observe the speed of light, no matter what frame of reference you're in, the speed of light is always the speed of light. So if you're inside that rocket with the flashlight, you would measure the speed of light to be c. If you were in that rocket looking at the flashlight, the rockets are coming towards each other, you would see the light coming towards you at c. Okay, the speed of light is a constant at all times. You cannot add to the speed of light. That's one of the fundamental rules of the universe. This is probably one of the biggest laws that exist in the universe. The speed of light is always the speed of light, no matter what frame of reference you're in, no matter if the frame of reference is moving or not. Okay, if the flashlight's coming towards you at 99.999% of the speed of light, it's still going to look like it's coming towards you at c. Even if the flashlight is going away from you at 99.999 c. If you see a light bulb, the flashlight's kind of directional, but if let's say a light bulb, that light bulb is traveling away from you at 99.999 c, you'll still see the speed of light as c. We do not add or subtract to the speed of light. That's a fundamental law of the universe. Now, what does this mean, though? This causes some major problems. Well, not problems really. Some major confusion in terms of causality and for example, look at this. Let's think about this train here. So the train is traveling at 99% of the speed of light. It's a very, very, very fast train. Okay. We'll see in this example that these two observers, the one on the train that's moving and the rest frame observer, we can no longer say that events happen at the same time. Let's imagine we're the observer on the platform. Lightning strikes both ends of the train, and from your point of view on the platform, you see those lightning strikes happen simultaneously. They happen at the exact same time. Okay, for you. Now, what are you going to interpret the observer on the platform, on the train, will see? So you're going to be on the tracks, you're going to be on the outside, and you're going to see things happening simultaneously. But you're going to see the rider moving at 0.99 c in this direction. But we know that the speed of light is constant, so you're going to be catching up. So let's say there's some sort of like light wave. These waves are coming. You're going to be going towards this one faster. So you will see that the observer, from your point of view, from the rest frame, you will see the observer see the light happen. The lightning strike hit the train at the front first. Okay, did you get that? So the two different observers have different viewpoints of simultaneity. It gets more confusing when you look at the person on the train. The person on the train thinks that they are at rest, and they are going to see the front flash first. Okay, so that's the front flash happens first, but what they're going to conclude is that it happened first. Okay, so this person on the platform imagines that these two events are happening simultaneously. The person on the train sees it happening with this one happening first and this one happening second. And they're going to see the observer on the platform, and this is now going to be the moving frame. This will be the rest frame in this case. So you're inside the train. You're going to be at rest. You're going to look out and you're going to see an observer going behind you. Okay? And they're going to see that the stationary observer is catching up to the right strike, so they see it simultaneously. Who's correct, though? So the observer outside here, this one thinks that happens at the same time, simultaneous. The person on the train thinks that the front happens first. Who is correct? They both are correct. Not only is there no absolute spatial frame of reference, like we said in Unit 1, right? That was one of the first things that I actually told you guys, is that we can't say that there's a correct frame of reference. All frames of reference are correct. Not only that, is there is no correct temporal frame of reference. The only constant is the speed of light. The only constant in the universe that we can say, the only thing that we can have absolute confidence in, is the speed of light. All right? So now, your brain probably hurts a little bit. You're going to have to watch this over and think about this. There's no mathematical questions for this unit. There's only 3 sort of thinking problems. This stuff took a very long time to develop, right? It took people like Albert Einstein and a bunch of other, very, very, very smart people. And we're still figuring out some of these ideas. Okay? The big idea, the big answer to all those questions, the big thing that we're going to figure out as we go through this unit, is that we'll never really end our understanding of physics. We'll always be learning more. There's always another step to go as we go through physics. We'll never stop. Maybe we will, maybe like some millions of years from now or something, if we still exist or something like that. But as we go through, we'll actually see that these questions these questions we're asking, the answers that we get to the questions, keep just producing more and more questions. All right, I'm starting to ramble. I apologize. So just work on these 3 questions. Think about the idea of simultaneity and moving observers. Think about what it means to be those flashlights. That's a really good thought experiment. Flashlights on rocket ships. How is it possible? What's the implications of the fact that the speed of light is always the same? How is it possible that the speed of light can always be the same? How can both observers be correct in their observation of the speed of light being the same? There's a way that we can do it, and that's what our next lesson is going to be. Okay, so now that I've confused you and hurt your brain, enough. That's the end of our first lesson here. All right, so hope you guys are doing well, and I'll be seeing you.